You know, when you walk into a hardware store and buy a tool, there's this strict implicit contract between you and the label on the box.
Right, yeah, like you buy a hammer, you expect it to drive nails.
Exactly. You buy a handsaw, it cuts wood. I mean, the name of the thing tells you the absolute parameters of what it actually does.
It's a guarantee.
Yeah, and in physical engineering, we really rely on that predictability. But in software engineering, well, that reliance on labels can create some pretty catastrophic blind
Oh,
spots.
absolutely.
Like,
Especially in the ecosystem of, like, strongly typed functional programming.
right, which brings us to the source material you, our listener, brought to the table for us today. It's part 211 of Ang's Notes on Haskell Programming.
It's a really fascinating deep dive into the ExceptT monad transformer in Haskell.
Yeah, and the mission for today's deep dive isn't just to, parse through syntax or learn a new library.
No, not at all.
We're dissecting a fundamental architectural trap. It's that dangerous gulf between what a typed abstraction promises to do and how the runtime environment actually behaves when things go wrong.
Because we build these massive complex architectures relying entirely on the type signatures of our tools, right? We treat them like mathematical proofs of safety.
Right.
So if a wrapper says it handles exceptions, we structure our entire application's control flow, assuming that it will, in fact, handle exceptions.
And when reality breaks that contract, it is rarely pretty.
To put it mildly, I mean, to really understand this trap, we first have to look at the architectural problem the author is actually trying to solve.
Okay, so take us back a bit.
Yeah, so in part 132 of their notes, Ang documented a struggle with something that they called the staircase of case.
Ah, yes, the notorious staircase.
Right. It's this very common pattern in functional programming, specifically when you're dealing with a sequence of operations that can, each individually fail.
Because in Haskell, you don't just return a raw value if something might go wrong.
Right.
You return an either type.
Exactly. So let's say you're building a file conversion pipeline.
Okay.
Step one is parse input.
Okay.
That function doesn't just hand you back your input data. It returns an either error input.
Meaning it could be the input or it could be an error.
Right. And to use that input in step two, let's say a parseDoc function, you have to manually unpack it using a case statement.
Right. So you literally have to write code that says, like, in the case that this is a right value, meaning success, grab the data and pass it to parseDoc.
Yep.
And in the case that it is a left value, meaning failure, just halt and return the error.
And you have to do that for every single step in the pipeline.
Wow.
So if parseDoc succeeds, you pattern match its result again to pass it to the next step, maybe convert to ebook.
So visually, looking at your screen, your code just starts indenting further and further to the right with each sequential check.
Exactly. You end up with these deeply nested, heavily indented blocks of code that look like a literal staircase across your monitor.
And your actual business logic, the stuff you care about, just gets completely buried under all this boilerplate error routing. Right?
It makes the code base incredibly rigid. It's so hard to maintain. So developers naturally reach for a monad transformer.
Specifically, ExceptT.
Right. Which acts as an early exit mechanism to basically flatten that staircase.
Okay, let's unpack this for a second. It's kind of like a relay race, right?
Oh, I like that. How so?
Well, without this early exit tool, if the first runner drops the baton, the other runners still run around the track pretending they have it, doing all these manual checks.
Right.
But ExceptT just stops the race immediately. The moment the baton drops, the race is over.
That's a perfect analogy. Except T basically overloads the monadic bind operator, the symbol that looks like a greater than sign and an equals sign,
Right.
to automate that whole pattern matching process.
So it's like an automated switch on a train track.
Exactly. You just define the main track, parse input, then parseDoc, then convert to ebook. And ExceptT handles all the routing under the hood.
So if any step yields a left value, it instantly routes the execution to the failure siding. It bypasses the rest of the track entirely.
Which is why developers love it. I mean, the code goes from this deeply nested staircase to a perfectly straight vertical line of sequential operations.
And the type signature becomes ExceptT AppRRIO.
Right. And that signature tells the compiler and the programmer a very specific story. It says, I guarantee that this block of code will either successfully execute the I/O actions, or it will short-circuit and cleanly yield an app error.
It provides this real illusion of total control over the failure states.
The happy path of explicit typed errors.
But here's where it gets really interesting. That illusion of control is exactly where Aang ran into a brick wall.
Yeah, a massive one.
I mean, the tool is literally named ExceptT, short for exception transformer. The type signature explicitly declares that it handles errors.
It does.
Yet, during development, the author hit a situation where the application just didn't gracefully short-circuit. It didn't yield an app error.
No, it didn't.
The entire program suffered a fatal crash, completely bypassing the ExceptT wrapper. So, if it's literally called an exception transformer, why is it blind to actual exceptions?
Well, the problem lies in a fundamental misunderstanding of what ExceptT actually manipulates. It really comes down to the critical distinction between an in-band return value and an out-of-band runtime exception.
Okay, let's clearly delineate those two concepts because this is where the abstraction leaks.
Yeah, so an in-band return value is pure data. When a function in Haskell evaluates a condition and decides to fail, it packages that failure into a data structure.
In this case, a left app error.
Right, and that data structure is passed cleanly back up the call stack. The execution thread is intact, the runtime environment is stable.
The program is just moving an envelope of data from one function to another.
Exactly. And ExceptT simply reads the envelope and routes it. It's a polite conversation within the type system.
But an out-of-band runtime exception operates on a completely different plane of existence.
Entirely different. When we talk about I/O in Haskell, we are ultimately interfacing with the operating system, right? Underneath it all.
Right, via the C foreign function interface.
Yes. So if you ask the OS to read a file, and the OS encounters a hardware lock or a permission denial, it does not politely hand back a Haskell data structure.
No, it throws a raw system-level signal.
And the GHC runtime catches that signal and just initiates an immediate stack unwinding.
The runtime panics. It just stops evaluating expressions, ignores the monad transformer entirely, and starts tearing down the call stack looking for a low-level exception handler.
And if it doesn't find one, boom, the application terminates.
ExceptT is completely blind to this process.
Not totally blind.
Going back to our train analogy, it's an automated switch sitting on the tracks waiting to read the label on the next passing car.
Right.
But a runtime exception isn't a defective car. It's someone cutting the electrical power grid to the entire train station.
That is exactly it. The switch doesn't fail to route the error. It just never even gets the chance to try.
Yeah.
The infrastructure it relies on is gone.
So the name itself, exception transformer, is really a psychological trap.
It is. It's a historical artifact of functional programming nomenclature. But in the context of system-level I/O, it's incredibly misleading. It strongly implies it handles out-of-band exceptions when it only handles in-band return values.
And Aang recognized this trap. They didn't just write the crash off as a fluke.
No, they did something really cool. They set up a controlled manual simulation to actively force an out-of-band failure.
They intentionally sabotaged their own environment just to bypass the wrapper. Let's look at exactly what they did, because this is fascinating.
The methodology here perfectly isolates the difference between application logic and OS-level reality.
Right, so Aang starts by opening a terminal and establishing a baseline file. They run the command touch tmp foobar.txt.
So this creates a standard empty text file in the temporary directory. The file physically exists on the disk. The metadata is registered with the file system.
But then comes the sabotage. They use the command chmod artmtfoobar.txt.
Stripping away all the read permissions.
Exactly. By utilizing chmod, they forcefully remove the program's ability to access the file's contents at the POSSX level.
The file is still there. You can verify it exists, but any system call attempting to actually open a read stream will just be aggressively rejected by the Unix kernel.
So with the trap set, Aang runs their console app, the XS2 book program, and they explicitly target that sabotaged file.
The command was stack run-ds pdf tmp foobar.txt.
Right. So the application spins up, it initializes the ExceptT pipeline, and begins processing. And what happens?
Well, if the name exception transformer actually meant what it sounds like, the program would attempt to read the file, hit the POSXX lock, intercept the failure, and use that early exit mechanism.
It will politely say, app error, can't read this, and exit cleanly.
Exactly. But instead, it just completely blows up.
The terminal output is this massive, unhandled crash. GHC spits out a Haskell stack backtrace, dumping all these internal execution frames.
And the critical line in that crash log reads, open binary file, permission denied.
So what does this all mean for the developer? That early exit mechanism didn't work at all.
It means the application's internal error routing was entirely bypassed. The OS-level denial just bypassed, except T completely.
Because the GHC-based libraries tried to open a binary stream, the OS returned a permission error, and the one time translated that into an I/O exception.
Right, which immediately initiated stack unwinding. The throw I/O call happened deep inside the GHC internals. The tool was looking for a polite, structured failure, but the ground just opened up beneath it.
To really pinpoint exactly where the mental model diverged from the mechanical reality, Ang performs this line-by-line code autopsy of the parse input function itself.
Yeah, and looking at the source code reveals how the program's type-level checks provided this totally false sense of security right up until the moment it crashed.
It centers on the contrast between two specific lines, line 37 and line 42. Let's break those down.
Okay, so on line 37, the code does a pre-flight check. It uses the does-file-exist function, lifting it into the monad using lift.io.
And this function basically just asks the file system, is there an inode at this path?
Right. And because Ang used the touch command earlier, the OS says yes. Does file exist successfully returns true.
Now, if it had returned false, the code would proceed to line 39 and call throw error, file not found.
And this is a crucial distinction. Throw error here is not throwing a runtime exception.
Right, it's just a function from the ExceptT library packaging the file not found tag into a left data structure.
Exactly. It's generating an in-band value. If the file hadn't existed, ExceptT would have perfectly routed that left value, short-circuited the pipeline, and returned a graceful app error.
The train switch would have worked perfectly. It's like a bouncer checking your ID and politely turning you away. That's a planned return value.
I love that analogy, yes.
Yeah.
But the file does exist. The POSX lock only prevents reading, not existence verification.
So the program passes the check on line 37, assumes the environment is safe, and proceeds to line 42.
And line 42 is the meteor hitting the nightclub.
Right. The bouncer has no protocol for a meteor.
At line 42, lift.io is used to execute bl.readFile. That's a function that attempts to physically load the file contents into memory.
And this is where we really have to look at lift.io because it's so often misunderstood as a safety net.
Yeah, people think lift.io magically converts raw system chaos into pure Haskell values. It absolutely does not.
It just takes an I/O action and embeds it within the transformer stack. It lets ExceptT execute the action, but it doesn't police how that action behaves internally at all.
So when bl.readFile triggers the open binary file system call, the OS enforces that quad-IR restriction we set up. The read stream is blocked.
And bl.readFile does not catch this OS signal. It doesn't return a left value.
It has no mechanism to do so. It just allows the GHC runtime to raise an out-of-band I/O exception.
And lift.io just watches helplessly as the exception rips through the transformer stack and crashes the program.
Exactly. So line 37 operates entirely in band. It asks a question, gets an answer, uses throw error. It plays by the rules.
But line 42 operates out of band. It triggers an OS operation that fails at the system level.
And that results in a stack unwinding panic that does not respect type signatures or monadic routing. ExceptT only manipulates values returned by functions, not exceptions thrown by the runtime system.
It's strictly a value shuffling tool, an organizational pattern for pure data, masquerading under a name that implies, robust system-level resilience.
Which really highlights a pervasive issue in modern software development. I mean, as we build higher-level abstractions to hide all these messy low-level details, we often abstract away our own understanding of the execution model.
We start trusting the names of our libraries more than we trust the reality of the operating system they run on.
Exactly. So the question becomes, if ExceptT is architecturally incapable of handling out-of-band system failures, how do you build a resilient pipeline that involves I/O?
Well, Ang points to the necessary paradigm shift at the end of their notes. They say it'll be the topic of their next post, actually.
You have to completely abandon the illusion that monad transformers handle system panics. You have to use true I/O exception mechanisms.
Specifically, you have to reach for the control.exception module, functions like try, catch, and throw I/O.
Right, because these aren't just value wrappers. They are direct bindings to the runtime system itself.
So when you wrap an I/O action in try, you are explicitly instructing the GHC runtime to establish an exception handler on the call stack.
So if we rewrite that meteor strike on line 42 to use try, we fundamentally change the flow of the failure.
The POSX read lock still triggers the panic. The runtime still begins unwinding the stack.
But before it can crash the program, it hits the handler established by try.
And try intercepts that out-of-band unwinding, halts it, and translates the system-level panic back into an in-band Haskell data structure.
Specifically, an either IO exception byte string. It bridges the gap between the OS reality and the Haskell type system.
And once it's packaged into a left IO exception, you can map that generic error into your specific domain logic, feed it back into the ExceptT pipeline.
You're manually restoring power to the train station so the switches can work again.
Exactly. You decouple the domain logic routing from the system-level error handling.
ExceptT goes back to managing the staircase of case for your internal rules and control. Exception handles the chaotic reality of the physical hardware.
You stop expecting one tool to solve two completely different categories of problems.
And that's why Ang's documentation here is just incredibly valuable. They didn't just patch the bug with a try-catch block and move on.
No, by manually recreating the failure with Tronit, dumping the stack trace, tracing the divergence between line 37 and 42, they mapped the exact boundaries of the abstraction.
They clearly defined exactly where the type system ends and the operating system begins.
It really is a phenomenal breakdown of how a widely accepted best practice can introduce severe structural vulnerabilities if you don't fully understand the underlying mechanisms.
It is.
I mean, you brought us a deep dive today that starts with a simple wrapper and ends with a fundamental lesson on stack execution and POSX interactions.
Yeah, you really cannot look at a tool named Exception Transformer and assume your environment is safe from system panics. You have to verify the mechanics.
Which leaves a lingering architectural question for you, our listener, to consider as you review your own code bases. We've just dissected how a standard tool acts as an automated track switch, cleanly routing internal logic while remaining entirely blind to the power cord being pulled by the OS.
Right.
So, how many other standard tools or best practices in your current workflow are operating under that same illusion? How many of your perfectly typed, elegantly named data pipelines are hiding dangerous blind spots? Just waiting for the right environmental failure, like a permission denial or a network timeout, to expose them and bypass your logic entirely.
It really requires a fundamental reevaluation of where you place your trust in a system's architecture.
Look past the type signatures and trace the execution. We'll catch you on the next one.